These are the results of an April 2026 benchmark testing frontier models on complex coding tasks. One setup scores 77%, the other reaches 93% accuracy. Both test environments had access to the exact same foundational model, Anthropic's Opus 4.6. The 77% score came from Claude Code, Anthropic's own environment, meaning the model underperformed inside its creator system compared to a competitor's. This 16-point gap is driven by a technical variable called harness engineering. A harness is a distinct software layer separate from the foundational model processing the tokens and the front-end user interface where the chat occurs. It is an orchestration layer consisting of tool access, system prompts, permission logic, and context management. As foundational models commoditize, the technical differentiator for production AI has moved into this execution infrastructure. It is often assumed that autonomous agents maintain a continuous stream of thought while executing tasks. In reality, they operate in a discrete mechanical loop. The model generates text until it hits a specific tool call syntax, hitting a hard stop. The harness intercepts this syntax, executes deterministic code, and returns text data. This output is appended to the history, restarting the model. Models possess no persistent state. They only know the specific context provided to them at the exact moment of the restart. Since agents are stateless between actions, the harness's ability to linearly accumulate and inject context becomes the defining factor in agent capability. Human engineers exert the most direct control over an agent through its tool descriptions. A foundational model cannot see the underlying source code of the tools it uses. It only sees the text explaining what the tool is for. If an engineer modifies a tool description string to say, deprecated, use bash instead, they are effectively reprogramming the agent's decision logic. This single string change produces different outcomes across models. Claude Sonnet might ignore the instruction, while Gemini instantly alters its tool selection pathway. Cursor's 93% benchmark reflects this continuous tuning process, where engineers micro-adjust text strings to align with the specific behavioral patterns of each model version. Tool descriptions are not documentation. They are highly sensitive behavioral prompts that serve as the primary control surface for production agents. The repo mix approach assumed that dumping entire code bases into an LLM context window would improve architectural reasoning. However, current models face a context budget accuracy cliff. This chart shows a vertical drop-off in performance between 50,000 and 100,000 tokens. Pushing past this threshold results in needle-in-haystack degradation. Latency increases and output reliability plummets, while API costs continue to stale. This requires an architectural shift toward active context budget management. This is achieved through a pre-compaction hook, a system that acts as a garbage collector, aggressively trimming bloated session histories during long execution loops. To maintain reliability, context compaction must be engineered as a first-class system feature rather than an ad hoc fix. These systems are moving toward a dark factory pattern, an engineering pipeline where human operators neither type nor review code before it ships to production. This is already operational at the Creo team, which maintains 3 to 8 production deployments per day with a 99% AI-generated codebase. Their architecture translates observability data into triage. Structured error signals flow from the monitoring node directly into a central triage engine. Discrete agents then handle isolated phases of repair, passing the fix through 3 parallel review nodes before it enters the merge queue. Dark factory automation introduces a specific security threat known as the lethal trifecta. This risk emerges at the intersection of 3 vectors: access to private data, ingestion of malicious external instructions, and outbound exfiltration capabilities. A properly configured harness permission layer neutralizes this by establishing strict human-in-the-loop gates for high-stakes outbound actions. In this environment, the senior engineer becomes the architect, a role dedicated to defining AI constraints and criticizing agent logic rather than writing syntax. High-velocity deployment relies on the rigidity of these permission gates and automated test loops, not on the inherent reliability of the AI model. The emerging standard for enterprise deployment is a local cloud hybrid routing stack. The first tier uses fast on-premise hardware for pre-processing, triage, and sensitive data handling. The harness then selectively routes only the most complex reasoning tasks to expensive frontier cloud APIs. Orchestrating this routing layer can reduce enterprise API costs by up to 40%. This is creating a market fracture between two distinct capability zones. Zone 1, general-purpose coding harnesses, is commoditizing as self-tuning meta-agents optimize against public benchmarks. Zone 2 contains specialized harnesses built for strictly regulated industries, such as healthcare and finance. This creates an eval moat. Because auto-tuning agents require quantitative benchmarks to self-improve, they cannot optimize for private, compliance-heavy workflows. While anyone can call an API, owning the proprietary evaluation benchmarks for a specific industry provides the technical barrier for production-grade AI.